So caches are the highest level in a memory hierarchy, as shown here. They are typically very fast, about 1 processor cycle time, and they ideally supply most of the data to the processor. So the processor it appears to the processor that the access time for memory is 1 cycle. It usually holds most recently accessed data. So when we design a cache, we talk about 3 questions. What data is held in the cache? How do we find data? And how do we replace data if the cache is already full and we need to pull more data into the cache? So in this discussion, we're going to focus on loads, but stores follow the same principles. So what data is held in the cache? Ideally, the cache anticipates the needed data and puts it in the cache, but it's impossible to predict the future. So we can use the past to predict the future using the locality we talked about earlier, temporal and spatial locality. We use temporal locality by copying newly accessed data into the cache. So if we accessed the data recently, that cache is copied, that data is copied into the cache so that we have that ready for the next time it's accessed. Spatial locality means that when we access some piece of data, we also pull in neighboring data, that is data in nearby addresses, memory addresses. So here's some cache terminology, and we'll use this through the rest of the discussion. The capacity of the cache, C, capital C, is the number of data bytes from the cache. And particularly, noteworthy here is to notice that this means the number of data bytes. Right? Because we're going to actually be storing some other information in the cache as well, but this is for the amount of data that we store in the cache. Block size, lowercase b, is the bytes of data that's brought into the cache at once. And this is also called, you'll see it referred to as the line size. The number of blocks, capital B, is the cache capacity, the total number of data bytes we can store divided by the block size, lowercase b. Degree of associativity, we'll talk about this, is n. This is the number of sets of blocks in a set. And the number of sets is each memory address that maps to exactly one location in one set. So set equals the number of blocks over the number, the degree of associativity, the number of ways. And we'll talk about both of those last 2 terms in more detail as well as the other terms. So how is data found? Data in a cache is organized into sets. So we have S, the number of sets, and each memory address maps to exactly one of those sets. Caches are categorized by the number of blocks in a set. And so a direct map cache has 1 block per set. An n-way set associative cache, also just called an n-way associative cache, has n blocks per set. And a fully associative cache is where all cache blocks are in a single set. So we'll examine each organization for a cache. This is a kind of toy example to demonstrate the principles, right? We'd never have a cache with only 8 words in it. But again, this is a toy example to just illustrate the principles. So the capacity for these example caches is 8 words. Block size is 1 word, so 32 bits. And the number of blocks is 8. So here it is written out, just in bullet points here. Capacity 8 words, block size 1 word, and so the number of blocks is 8.